Hey, welcome to day 20 of the Advent of Code challenges. Wow. So today's one was interesting. I have already done it. So this is going to be another explanation video. But this was interesting because when I first read the problem description, I thought I would be able to do this live. And they threw in a little twist that meant that um, I couldn't finish it live. And so I had to finish it. And then now I'm recording again to explain how I did it. So I'm going to assume, as before, that you've read the problem description, you understand kind of how it goes. The problem is very reminiscent of Conway's Game of Life. Um, in fact, most of the programming felt very familiar because I coded up a Conway's Game of Life engine before. And so I guess I'll just walk through my thoughts as I did this. So the first thing is, of course, how do I represent the data in memory? But for this specific one, I decided that what makes the most sense is to use a sparse set of um, on pixels, right? So the easiest way to represent that is something like if I had a map of points, which I'll call xy, something like this. And then what I could do is I just need the xy type now, which is going to be a struct of, you guessed it, x and y. Something like this is really nice to represent a grid because you can go negative, you can go positive, you don't, you'll never run into out of bounds errors. And the best thing is because of zero values in Go, if a specific xy value hasn't been entered into the grid, because the data type here is bool, I'm just going to get back false. So in that sense, it's kind of very similar to JavaScript in that using this sort of data type will mean that I can always index with no issue. At least it won't crash, I mean. And in this particular case, based on this example, it will actually give me the values I want because anything I don't put in will just be false by default. Now, if you've already looked at the puzzle and you've tried to do it, or you've already done it, you'll know the problem that you'll run into later. But yeah, so I'll just keep going on this track for now. So it's very straightforward to add something into this particular structure. We're just going to say for every row in starting from the second line in my data, and then for every character or value in the row, if the value is a hash, then grid, and then the struct xy equals true. Then if we print out the grid, we have it. And then so what I decided to do at this point was it would be nice to be able to print this out in a nicer way. So to do that, I kind of needed a little bit more information in my struct. So I ended up turning it into something more like this, where I stored the min and max x and y of all the values I've added into the grid, which will give me a bounding box. Then I can print out just that area. Now to keep track of the min x and y, then now I need a function which I will call flag instead of on and off for reasons that will become evident later. So maybe a point xy. No, yeah, maybe a point xy like this. So then here it's quite straightforward. G dot grid. The point is true, and then we just do this whole testing thing. If you're smaller than min x, then min x equals x. If you're bigger than max x, and so on, right? so that gives me a bounding box when I add stuff. So I just need to make sure that over here we're actually doing that. Yeah, to make sure that we initialize things properly, I just need a new grid function that will return me a grid that's initialized correctly. So like that. So I get a new grid. And then if this is the case, then grid dot flag that, right? Cool. So that should still do the same thing. Right. Okay, this is going to take a little while. I'm just going to pop these in. Oops. Cool. So that should work. Great, but now that I have my bounding box, so nothing has changed, it still runs, which is what we want, but hopefully those min-x and max-x's are correct. So our trusty string function now use a string builder for this kind of thing because you want it to be relatively efficient. So it should be quite straightforward, right? For y from min y, and I just gave it a -1 here just to give it a little bit of context to see the surrounding. Less than or equal to max y. Less than or equal to because the max is inclusive, not exclusive in this case. And then here we do the same thing, but for x. So we just have our box and then we just print it out, right? If g dot grid x, y, then if it's true, we write a hash, and if it's false, we write a dot. Then we just need a new line, and we return the thing. And so now we have this nice kind of print, and you can see that it matches exactly the test data. Oh, I've already copied the test data into this at the top. Oh, sorry about that. Hope you don't hear the cars outside. So yeah, so that makes sense. And then now we just have a step function. This is very, like I said at the beginning, very reminiscent of Conway's scheme of life. Now the important thing about the step function is we want to, because of the way that these are 3x3 grids, right, we need to check not just all the values that are on, right, but also all the values that are, all the points that are around all the values that are on. So for example, I need to check, I wonder if I can do like this sort of select, like I need to check this, right, which is centered on this, which is centered on this dot, which is around the value that is on. And so in order to do a step, and this is going to, yeah, this is one of those cases where I don't want to mutate it. One of the very common mistakes is when you're updating Conway's Game of Life sort of grid is that you update it in place, and that doesn't work because that messes up all your other calculations. So you have to make a new grid here. So I call it, just call it next. And then what do? We say two loops. The first loop, we get a list of all the points that we need to check. This is actually a set, but I'm going to use bool anyway because I've mentioned this before in my previous ones. Using empty struct here is just harder to read for me. So I prefer to use a bool even if I'm representing a set. So this is the easy bit because we already know all the points that are on, it's just all the keys that are in the grid. And so for every key in the grid, we just say to check, we add x minus 1, y minus 1, then x and x plus 1, x minus 1, x plus 1, x minus 1, x plus 1, and then we just go y minus 1, y, and y plus 1. So those are all the 9 points around around every point, right? That should make sense. For things like this, I like to just write it all out. You don't have to always use loops, especially when it's a small thing like this. And then for every point in the points that we need to check, we need to get the value, right? So a couple of things. One, I'm just going to pass in the string here into the step function because we can just index into it. This was the easiest way for me to pass the string around. I guess you could save it into grid as well, but I just liked it like this. The other thing is we actually need a helper function to read a value from a grid. So to read this thing, they tell us how to do it. You just have to read through this, pretend this is the most significant bit. So most significant, next most significant bit, and then so on, all the way down to the least significant bit, and hashes of ones. So the easiest way to do this, for me, the first thing that came to mind was to just do a loop and then just keep pushing ones over as you read. What do I mean by that? Let's see. So yeah, here I did use a loop. Y equals p dot y minus 1. Yep. All the way to p dot y plus 1. And then from, p dot x minus 1 to p dot x plus 1. We shift out up by 1, and then we put a 1, tack a 1 on the end. If x, if that value is a 1, if that value is true. Yeah, and then you return out here. Okay. Because it's easier for me to write like this. Missing a return here. P declared but not used. Great. So I think this is right. Hopefully that little algorithm makes sense. We're just building up the bit string the way that they describe here as we're reading those values out of the grid. And then, so we just say the index is going to be g.read index at p, which is just going to give us that index. And then if enhance idx is a hash, then we set the next grid, right? Next dot flag p. Return next. So that should just do it. And we can test it here quite straightforwardly by just saying step and then passing in the enhance algorithm string. And you'll see, yeah, after one step, it now looks exactly like the previous one, the next one like it's supposed to. And then if we step again, oops, 0, we get the next one. So that's all good. It's a relatively straightforward algorithm to code up. Nothing too crazy about it. But of course, they throw in a little curveball, which is, and I'm assuming they did this with everyone's inputs, was that in the example they gave, 0 returned a dot, which is off. And so this algorithm would work because everything that's beyond what we know is just always off. But in the actual test input for, and this is the bit I'm assuming for everyone, they made that on. And so after one loop of the algorithm, everything is going to be on, right? The default, so there will be an infinite number of lights that are on and only a specific number of lights that are off. But it's okay because they'll also set the final one back to off, which means if everything was on, one step later, everything is off again. I hope that makes sense, right? Because if this, right, according to the algorithm, using this input string here, one step later, this is going to turn into an on. So then everything is going to be on. And then when this is all on, but when this is all on, it's going to become off again because this is, the number 511, which is going to be the final one. So one step later, it's all off again. And so they kind of trick you, especially if you've implemented Golang Scheme of Life before. You kind of don't really think about this. You just assume things that are off are just going to stay off. And they threw this little curveball in. This was where I realized I wouldn't be able to finish this live. Because I was also in a little bit of a hurry, and with that pressure, it was really hard to think clearly. But it turns out it's not too hard. You just have to keep track of whether the default value is on or off. So when we start off, we say that the default value is off. Everything not within that we can't see, that isn't labeled, that isn't in the grid in the grid map, is off. And then one step later, we flip this around and we say everything that's not in the grid map is on, and everything that's in it is actually off. And that's actually kind of why I called this function flag, because this no longer indicates whether things are on or off. It actually indicates whether it's not the default state. And so that's how I chose to represent my data structure in memory. So how do we do that? Well, a couple of things. First, I actually wrote a test case for me to just make sure that the algorithm is working. So this is my test case. It's just a very specifically crafted string which will output a specific pattern that I worked out on a piece of paper, like this, just so that I would be able to test my input. So let's see what's going on here. Okay. So after one step, I should get this pattern, but this pattern is actually wrong because all of those values at the edge, they should all be false. Sorry, they should all be on, right? Because by default, this string has a hash at the beginning, which means all the zeros should now be ones. And so this is why this is wrong. And so there's just a bunch of things you have to go through and change it. To change it, first thing, the grid needs to keep track of whether or not this is what the default is. So we have this. Default is going to be a bool. By default, the default is false. I'm just going to put this in here, even though that's set, just because I want to make sure that that is clear. So all of these functions just need a little bit of a change. First, the string function. This is quite straightforward. If the value is not the default, then we print out a hash, I think. Let me just double check against my other one. And I printed it out. Yeah, if it, right, yeah, okay. I'm not sure if this is actually the same or if it's different. I also added a little bit an extra line in here. You'll see actually. Why don't I just copy it? Which will just show me what the default is when I print it out. So this is still wrong because after one step the default should be false. So where do I do that? So here we have to work out what the next default should be. And so that's actually quite straightforward. If the current default is all zeros, then the default should be whatever's in index 0 of my enhanced string. If the default is 1, then my next default should be whatever's in the 511th index of the string, the final one, because that's what that will refer to. And so we can write that by saying next.def equals so a couple of things. I think we'll start with what the default should be. Default is going to start off as whatever's in 0, but if the current default is actually 1, if current default is true, then the default becomes the final thing. So then next.default is just going to be if default is a hash. Is not a hash? Yeah, if it's a hash, because if it's hash, then the next default is going to be true. So that's the first thing that needs to change. The second thing that needs to change is when do we flag things? And we flag things when it is not equal to the next default, if that makes sense. Because if it's a default, we don't need to flag it. So we only flag it if it's not the default. So it's a little bit, these Booleans are a little bit hard on the brain sometimes, but that should be good. So that's the step function. And the final thing is this read index function, because now depending on the default, all our ones are actually zeros. All the flags are either ones or zeros, depending on what the flag is. So once we read out our number, we actually need to flip it if the default is true. And so we say if g.default is true, then we just need to flip our number. And to flip our number, we can do a not, and then we just need to mask it out, because otherwise it'll turn into a negative number. This is bitwise not in Go. So as you can see, now that we have now we have a representation where the default is true and all of this. And so just taking a couple of steps with my specific pattern, what will happen is this is kind of like a Conway's Game of Life glider. It will keep moving to the right. I just designed it like that, so it was kind of easy to see if my implementation was correct. This should be 0. So it should turn back into a single dot, but now it's moved over to the right. Now it turns back into this pattern. And then it should turn into another dot, but this is, again, further to the right. And so that was basically the rundown of the implementation. It's just about keeping track of the default, and then depending on what the default is, changing the algorithm around a little bit so that it's handling the data correctly. So we're going to get rid of the test data, and we are going to just run it on the actual data. And you should see that, oh, we need to count. We need to count the thing. And now counting is easy because the questions always ask for on an even number of iterations. Here we go, twice. Even number of iterations, because if it's every odd iteration is going to have an infinite number of ons, and that won't make any sense. So in an even iteration where the default is off, everything in the array is just going to be the points that are on, and so we can just get the length of the map. I said array earlier, I meant map. So 5,400, as you can see there. And then the second part, it just says run it 50 times. That's not hard at all. That's literally run it 50 times. Like that. And then we do the same thing. Whoops. you run it 50 times and you get 18, you get your second answer. Um, so yeah, so that was my solution. It was just that little wrench, a spanner in the works with the default thing. But once you figure out a way to toggle, once you've identified all the places where you need to toggle between default true, default false, the whole thing just works. And yeah, 50 times doesn't seem particularly hard. I'm not sure what kind of implementation requires would make that hard. So yeah, it was an interesting challenge. It was one of those challenges I thought I could do live, and then with that little trick, it just kind of I had to sit down and think about it for a second. Um, yeah, so it's actually local time 5:40 in New Zealand, which means it's 20 minutes until the next one, but I won't be able to do that until much later tonight. And so I thank you for watching this video, and I will see you again next time.